Yes, welcome back again to my channel. This is still Sajut Lectures. So today we'll be looking at a second example on mathematical induction. So still a mathematical induction, example 2. So the example 2 said we should prove that for any positive integer, prove that for any positive integer n, 1 squared plus 2 squared plus 3 squared plus ... plus n squared is equal to n into n plus 1 2n plus 1 all over 6. So this is an induction problem of which we are supposed to prove. Now, like I taught you in the previous video that when you come to induction problem like this, I say mathematical induction have 3 major steps we use. So we're going to apply the 3 major steps. And the step 1, like I taught you initially, is called the basic step. So let's look at the case 1. Case 1 is the basic case, that is when n equal 1. So then we have our p of 1 is not going to be 1 square plus 2 square plus 3 square plus. So you notice that, like I told you before, instead of putting 1 square here, we say that this is just a term that make up this function on the right hand side. So this is equal to, now here we have n, so n is 1 into another n plus 1, that is 1 plus 1, then into 2n plus 1, that is 2 into 1, then plus 1 all over 6. So now let's check whether it satisfies, because that is the major thing that we do in mathematical induction. We prove the steps to see if it holds. Okay, so when we have this, you notice that on the left hand side we already have 1 on the left hand side. So we have this to be 1 squared is equal to, so we have here to be 1 into 1 plus 1 is 2. 2 times 1 is 2 plus 1 is 3 all over 6. So here we have 1 squared is 1, which is equal to 1 into 6 over 6. You notice, so this implies 1 is equal to 1. Thus, the basic step holds for the mathematical induction. Now let's go to the second step, which is the inductive hypothesis step. So let's look at the inductive hypothesis step. So for the inductive hypothesis step, we said that is the case 2 when n is equal to k. And I said this is pretty much easy. Just replace it. 1 square plus 2 square plus 3 square plus ... plus. This is n square. Here we have now k square is equal to n here becomes k. The other n is k plus 1 now. So this is 2k plus 1 over 6. And you are done with the what? The case 2. That is the inductive hypothesis step. So next we go to the case 3. That is the major work we have. That is the inductive step itself. So the inductive step is to prove. Inductive step is simply when, that is the case 3, where n is equal to k plus 1. So we have p of k plus 1 will now be 1 square plus 2 square plus 3 square plus ... plus. So here it was k squared, then add what? K plus 1 to it, square it. Always remember that the term that is left, you have to add it up to it while proving the inductive step. So this is now equal to what is on the right hand side is going to be k. Here is now k plus 1. So here we have k plus 1 initially, that is k plus 1 now is going to be k plus 2. So here we have 2 into k plus 1 plus 1, then everything over 6. So that is what we have. So from here now we are going to recall something quickly from the step 2 we just erased. So from step 2 we just erased, we have to recall that. We need to recall this very fast. We are going to use it to prove this. So recall that initially we have that 1 square plus 2 square plus 3 square plus ... plus k squared. We said it was equal to what? K into k plus 1 to k plus 1. Okay? So everything over 6. So we are now going to look at, from here now, you see that this is actually equal to what we have up to this point. So then we're going to use this now to replace all these things. And then we're going to be adding it to what? K plus 1 squared. So now let's do that. First, we're going to have this to be, we have the function by this side is going to be now k into k plus 1. So let's have it here. So this is now going to be k into k plus 1 to k plus 1 over 6. Then it's going to be plus k plus 1 what? Squared. So now we want to prove that this at this other left-hand side is going to be equal to what we actually will obtain at the right-hand side. So now we're going to simplify. So, but first of all, I would like you to be very careful before simplifying something like this. Now we maybe distribute 6, that is to make it k into k plus 1. This is 2k plus 1 over 6. So we distribute 6 to make it this way over 6. Okay, so I have not changed anything, so that 6 can cancel 6 to give me back this one. So I have not changed anything yet. All right, so we have not changed anything. Everything is still correct. So now let's continue solving. Let's make more space at the top here. So proving this now, what we do here is simple. We try to see, okay, now look at this. K plus 1 appears here, and here it is squared of it. So we can start to factor out k plus 1. So we have it outside. Next we have k into what? What is left is 2k plus 1 at this side over 6. Then what is left here is, this is now going to be only what? K plus 1 left. K plus 1 over 6. So you see, we are progressing. So after this, next thing we do here is we keep simplifying. Let's have it. This is still k plus 1 outside. So we still have k plus 1 here. So this is k plus 1 into this bracket. So now let's simplify. You notice this is now multiply k into it. We have 2k squared plus, this is 2k squared plus k. Then this is plus 6k plus 6 over 6. So all of them have the same denominator now. So we have to make them this way. So next, we look at this. We can add up what is at the top here. So that is k plus 1 over, we can factor 6 out also. So that we can have only 2k squared plus 6k plus k is 7k plus 6. So we are at this point now. Okay, let's create more space at the top so we can continue our solving. Our proof, yes, though it's still solving. So next thing you do from here is simple. We now look for what can factor into this quadratic equation here. All right. So if we now get it, it will be k plus, now we have k plus 1 over 6. If we factor this quadratic equation, there will be two values of k, but now we have 2k. So let's say this is k and this is 2k. So what can give us 6 here? 3 times 2 can give us 6. 6 times 1 will give us 6. But if you use 6 times 1, you won't obtain, you're going to have something very cumbersome that you can't reconcile. So we have to make use of 3 times 2. Okay? So, and all are positive, so we have to put it positive. So that if we open up this bracket, we're going to obtain exactly this. Okay? So if that is the case, it means that our final working now, that is the proof. Let's look at this. So now let's write this proof very well in a way that it will be more understood. Okay, so we have this is now going to be what? K plus 1 into k plus 2 into 2k plus 3 over 6. So this is what we got at the left hand side. Now remember something quickly. Please keep this as aside so that we can recall something quickly. Let's just go back a little bit. That when we say let n be equal to k plus 1, what we had was 1 square plus 2 square plus 3 square plus dot 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 plus, okay? Now this is not going to be what is at this side is now equal to, so over there we have k plus 1 into k plus 1 plus 1, then into 2 into k plus 1, right? Plus 1. Yes. So this over 6. So here if we simplify this, what do we have? We're going to have k plus 1 into k plus 2, then into, what do we have? So this is going to be 2 times k is going to be 2k plus 2 times 1 is 2, plus this one is going to be 3, all over 6. So you notice that this equal to this. So that is what we do in mathematical induction. So the left-hand side is equal to the right-hand side. Thus, we have proved that the statement is correct. And hence, that ends our proof of this inductive statement. Thanks for watching this video. This is Extreme Learning website. This is Sir Jude lecture. Sir Jude lecture. Do well to subscribe. Thanks.